Okay, hello everyone. Welcome to the SI session. So just a little bit before we get started, is that since this is an alternative virtual SI session, you're going to have to keep your videos and then mic on mute. But for the agenda, this is what we're gonna do. We're gonna do a little bit of a recap from this chapter, like what we have been covering so far. And what we have covered in the chapter so far. So we'll just list a few things so we can check off what is something that we have already done. And then we will do some activities where you will determine whether a molecule is nonpolar, polar, or ionic. And then we'll do some shapes and polarity problems. So we have done the shape component in my previous session, but we haven't done the polarity portion of it. So we'll just get started from there. And then we'll do a closing where we will kind of list a few things that we learned during the session today. But does anybody have any questions before we get started? Okay, sounds like no question for now, but if you do have any questions that come up later on, please let me know. It's okay if you're on your way to work or home, it's totally fine. So for now, we will just do like a recap of what we have been covering so far. So can you guys list a few things that we either covered in our SI sessions or in our lectures so far? How about nomenclature? So we have done nomenclature for what kind of compounds? So we learned diatomic molecules or elements. Yeah, this was like the phrase that I used last time. So make sure you know that, kind of like a mnemonic to memorize it. Yep, we went over the octet rule. So that was good. Yes, ionic. We covered ionic and covalent compounds. Thank you. Yeah, so we did nomenclature, like going from the formula to the name and from the name to the formula. Okay. And then you guys have done some polyatomic ions as well, right? So yeah, here you go. So polyatomic ions. So basically for the polyatomic ions, you don't have to necessarily memorize them. You will just know how to use them. And we have done that in the past, but we will do some reviews later on as well. Yeah, we did some prefixes. So those prefixes were something like mono, di, tri, and so forth. So make sure you look at your notes for that. Okay. Yeah, so today this is what we're gonna go over. We are gonna go over molecular polarity. And we will also be trying to determine whether something is nonpolar, polar, or ionic using the electronegativity. So I'll just put this in the parentheses so you know how we are determining them. Okay, so I'm going to share this document with you guys. So you can also get an access and then edit it. Right, so I just added the link to the document in the chat, so make sure you open it up. But for the students who just joined in, just to let you kind of recap, these are a few things that we are going to be covering today. We are going to be determining whether a molecule or a compound is nonpolar, polar, or ionic. And then we'll do some on determining the shape and the polarity of molecules. And then we'll do a closing where we will just debrief about what we have covered so far in the session and then how we feel about it, how comfortable we are with the content. And then these are some of the things we have been covering in our chapters so far in this unit that will be on your midterm, the second one. So, but today we are going to be doing electronegativity. So I just added the cutoff numbers. So can somebody tell me when we have electronegativity between 0 and 0.4, is that nonpolar, polar, or ionic? And you can drop that in the chat. Yep, I have one answer. Let me get a few more students to reply. Good job. So it is in fact non-polar. And then can somebody tell me what's if the electronegativity is between 0.5 and 1.7, is that polar or ionic? So we have only two options left. Yes, it is in fact polar. Thank you. Okay, and the last one is ionic. Yep, that's the only one left here. Okay, so now that we know this, I want you guys to look at these practice problems right here. Basically, what they're saying is identify the type of bond between the following atoms. Do we have a non-polar covalent bond? We have a polar bond, or we have ionic bond? And if the bond is polar, determine which atom has a negative partial charge. So I'm gonna give you guys a few minutes to do this on your own. So you're gonna have to look at the electronegativity chart, and then you can find that in your Canvas, or you can just do a generic Google search. And I'll try to put the link to the Google search as well. So just these few. Okay, so just to let you guys kind of get jump started on this, I'll do one problem and then the rest of it you guys can try to attempt it on your own, and then we'll see how that goes. So the first one we're gonna do is SO2, right? First let's see if the electronegativity is gonna work in our favor. So first we're going to find sulfur. So sulfur, can somebody tell me in the chat what's the electronegativity of it? So you will look at the chart right here. Yep, it is 3.5. Let me see. Yeah, it's 2.5. It's right here. And then we are going to find what's the electronegativity of oxygen. Can somebody tell me the electronegativity for oxygen? 3.5, yep. And now we are going to find the difference. So what's the difference between them? 1. So if it's 1, what category is it? Is it non-polar, polar, or ionic? Polar. Yep, that's right. And now they said if something is polar, they want us to know what's the partial negative charge of it. So when we kind of do like a Lewis dot structure or electron structure of this figure, we have the arrow going to oxygen or to the sulfur. Let me get one more person. So go from the center element to outsides. So when the arrows are going outside, it's usually that this charge is negative and this one is plus. So therefore the negative charge would be oxygen. And I'll just add the picture here. Does that kind of make sense to everybody? And this, you have to find the partial charge only for when it's polar, not when it's non-polar and ionic. Let me see the chat. Yeah, so basically, this is kind of to balance it out. If you're kind of confused about why is it plus or minus, it's kind of like when we are balancing these elements together. So which bond is stronger? Is it the sulfur that's stronger or oxygen? Oxygen is pulling the electrons from the sulfur and then taking it to itself. So the attraction force of oxygen is stronger over the sulfur. That's when we kind of use these arrows. And make sure you are not just looking at the, yeah, usually the central atom is going to be stronger. But sometimes you have only 2, like you could have just 1 sulfur and 1 oxygen, then it might be different, right? But I think we're probably gonna get a problem similar to that, so we'll do that when it comes across. But for these two, when you have like an equal, so the way I like to think about it is if I cut this in half, right, I'm gonna have equal of 2 things. So that's why the attraction force is going to be equal 50-50. But when you have only 2 elements that you're playing with, oxygen is going to get all of them. So oxygen is going to have a stronger pull than sulfur. And then also, so here you're not just looking at electronegativity, right? Like electronegativity is telling me it's polar, but you also look at something like this. You look at whether it has like the lone pairs. So make sure you're doing all of that. I know Dr. Tran, like she created a chart, which has all 3 things that you should be aware of when you're assigning something as like polar, non-polar, or ionic. But good job up until here. So make sure you draw the Lewis structure and then see if it matches with your polarity. And if I feel like an answer is incorrect, I'll highlight it so you can kind of give it more attention as like a whole. Okay, looks like we have a question as a whole class. It's about O3. So basically you can't really necessarily use electronegativity to find the answer, whether it's polar, non-polar, or ionic. There's another way to find whether something is polar or non-polar. is you draw the Lewis-Strauss structure of it, and then if you do have lone pairs, so I'll kind of write it here as notes. So if you do have lone pairs for the central atom, it's going to be polar. If you don't have any lone pairs, then it's going to be non-polar. So let me find the Lewis-Strauss structure of O3. Okay. Let's just open this one. Okay. It's basically the same resonance. You can put the double bond here or here. It doesn't really matter. But for the purpose of finding whether something is polar or non-polar, is you look at the central atom. So you have 3 oxygen, but this oxygen is my central, seen here. Since this oxygen has 2 lone pairs right here, it's going to be polar. And you can do that for any other element or compound as well. So if it has lone pairs, it's going to be polar. Is that clear with everybody? And also one piece of kind of advice, if you don't have any lone pairs, it's automatically non-polar as well. For the purpose of this class, we are not going to dive deeper into polarity, but as long as you know like whether how to find the electronegativity, how to find the attraction force, or something like this, and whether you know it's equal. So we can do like a similar thing for SO2, right? So let's see. SO2 Lewis dot. So here you can see that this has the lone pairs, right? So if it has lone pairs, is it going to be polar or non-polar? Polar, yep. So this one does. NO2, it's basically the same thing, so you don't have to worry about it. And for when you have ionic, when you have electronegativity for more than 1.7, you can always assume that it's ionic. Usually one distinction is it's polar ionic, but we don't have to dive into it for this class. Let's do H2S, right? H2S dot. Okay. So now you kind of have 2 things right here. Will that notate as polar or non-polar? So sulfur has these 2 lone pairs. Polar, yep, good job. Let's see what else we have. We have CF4 dot. Okay, does the central atom have any lone pairs? Yep, since it does not have any lone pairs, it's going to be non-polar. So these are some different ways you can find whether something is polar, non-polar, or ionic. I looked at all other answers. The answers look great. Let me make sure one last time. So polar, non-polar, ionic, polar, non-polar, polar, Okay, now the question is, can you tell if something is ionic by looking at the Lewis-Strauss structure? So ionic is a little different. Ionic, first you want to kind of find out whether it's between non-metals, metal, or non-metal, non-metal. So does anybody know? I kind of went over it last session, but we can add it to the notes section. It's more of like when you have covalent and ionic, what's the difference? Covalent bonds are between non-metal metal or not metal metal. I said it wrong. Let me write it. Non-metal plus metal is what? And then what is non-metal plus non-metal? Yes, you are right. So non-metal metal is ionic, and this one is covalent. So which one was ionic? Let me look. So K3N, right? Let's look at the periodic table. Like, I really actually like this periodic table. I can put the link here. The reason why I like this periodic table, it kind of tells you the answer. If I look at K right here, it will tell me that it's alkali metal. And it tells me the energy level, the electronegativity, all other things. Like most of these things you don't need to necessarily know, but it just helps. So you have K3 and N. So nitrogen is right here. So nitrogen is non-metal and potassium here is metal. So since it's non-metal metal, it's going to be ionic. So that's how you can find out. Okay, so now we can go to this. So I'm not sure if all of you guys attended my session where we drew the Lewis-Strauss structures for all these three. But for the time that we have left, maybe we'll spend like 15 minutes on this. What you can do if you need practice on Lewis-Strauss structure, draw the Lewis-Strauss structure and tell me whether it's polar or non-polar. Hint, there is no ionic here. And you can, and since we are trying to find the molarity of a molecule, like the whole molecule, you're not going to be using the electronegativity. For these ones, we were trying to find what's the bond between two elements. So whether carbon and fluorine, what's the bond that's between them. But for these ones, we're trying to find it as a whole. Wait, we're trying to find what's the polarity of the whole molecule. So it's the polarity of NF3, not between N and F, okay? So we're not gonna look at any attractions. We're not gonna find the negative or the positive charge. What we are going to do is we're going to draw the Lewis-Strauss structure. If it has lone pairs, it's polar. Okay, looks like we're almost done. It's okay if we were not able to get through all of it. We'll just go over what we have so far, and then since we have only like 2 minutes until this activity, we'll do like a closing. So let's go over the answers. Okay, so as you guys know, first we do like a Lewis dot structure. We try to determine the shape. So I will put the shapes here either way, but last session we determined the shapes, and then now we are just determining whether it's polar or non-polar. So what you can do if you were not in the session where we determined the shapes, I would suggest you to kind of not look at the answer necessarily, try to do it on your own, and then match your answers and see if you did it right. So this one would be pyramidal, and this shape looks perfect the way it is. And then since we have a lone pair, it's going to be polar. So that's good. And if you do have any questions that come up while I'm explaining something, please put that in the chat. And then this one, since SE has these lone pairs, it's going to be polar, but the shape of it, it's bent. As you can see right here, there is a bent because of these two lone pairs that we have. HBr, it's a linear shape, but since the BR has all these lone pairs, it's going to be polar, but the shape is linear. Okay, and then we have SIB4. So it's actually non-polar. Can somebody explain why it's non-polar? Looking at the Lewis structure right here. Yeah, so it does not have any lone pairs, especially the SI right here. So we are going to look at only the central atom. We're not going to look at BR. Some of you probably thought that, oh, BR has these lone pairs, that's why it's polar, but we're just going to look at the central atom. So Si. So silicon doesn't have any lone pairs, therefore it's non-polar, but the shape of it is tetrahedral. Okay. Any questions about what we have covered so far? Okay. And then we have H2O. So the central atom here, oxygen, has the lone pairs, therefore it's going to be polar, but the shape of it's bent just like the one we did previously. So these two lone pairs aren't going to make it bent. Otherwise, if you were doing it, you would think that it's linear, but because we have lone pairs, it's going to be bent. And then we have PF3. Yes. So here we have these lone pairs, right? Because of this lone pair on phosphorus, it's going to be polar, and the shape of it is pyramidal. Okay, and then CCl4. Let me kind of drag a picture from the internet for you to visually see it. Carbon. Is everyone kind of getting what we are talking about here? Okay. Right. So here's the Lewis dot structure of it. You can kind of do this on your own. Let me drag it down. Right. So CCl4 looks like this. Now, since carbon does not have any lone pairs, what is it going to be? Is it going to be polar or non-polar? non-polar because we have no lone pairs for carbon, and it's going to be tetrahedral. Okay. Now Br2. Yes. So since this one, like you might say that, oh, I don't know which one is the central atom. How is it going to be? It has these lone pairs. But since it's like the equal amount, it kind of cancels each other out. So kind of like what we were covering before. So it is going to be, in fact, nonpolar and linear. So good job. Polar and bent, this is good. Let me quickly find the Lewis dot structure of this. H2, Cl2. And if you are still kind of confused on how to do these kind of problems, like how to do the Lewis dot structures, like I would really suggest you to do this like on your own over like today, Sunday. Because as we kind of go into like Monday, we're gonna start talking about like balancing equations, and it's just not going to cover Lewis dot structures at all. So make sure you kind of have a practice. And then if you do have any questions, please bring those questions to the SI sessions. Okay, so this is how it's gonna look for CH2 and Cl3. You just put the chlorides on the same side, like on opposite sides, and then hydrogens like this. But since carbon doesn't have any lone pairs, it's going to be non-polar. But tetrahedral. Okay, and then even though we don't necessarily have time, but I would like everybody to kind of put something in the chat, something that like a topic that you learned today or any fact that you learned today, that you should, that's basically your takeaway from this SI session. But I will stop recording. But thank you everyone for coming to the SI session and then sharing answers.